I wrote a bunch of theory for section 4.3, and now I'm debating on whether to just explain the theory and do the problems or just do the problems. And I'm going to start this video with touching on the theory a little bit, and then if it feels like it's getting too deep, maybe I'll just go into the actual how we're going to solve the problems. What I wrote feels understandable, but until I start lecturing, I don't really know. So each function that we've found the derivative for this semester, it's written to like y equal to something, or it was written as f of x equal to something, or maybe we even had like a g of t equal to something. But it was either written solved for y or written in function notation. And we learned a handful of derivative rules: product rule, quotient rule, power rule, chain rule, how to find derivatives of e's, how to find derivatives of ln's. And in each one of the problems that we've done so far, we can say the function was explicitly written in terms of x or possibly t, that the variable that we were taking the derivative in terms of was written to the right of the equal sign. And that made the derivatives, maybe messy at times, but kind of straightforward. But sometimes we're going to be asked to find the derivative of functions that are written in more complicated forms, where it's difficult, if not impossible, to express the function in terms of x. This kind of function is called an implicit function, where it's not solved, it's not written in function notation, it's not solved for y in terms of x, yet I still want to find the derivative like it was solved for y equal to some function of x. Here's a few examples of implicit functions. So none of these functions is solved for y are written in function notation, meaning the x isn't isolated. The x isn't by itself on the right side of the equation. The y isn't by itself on the left side of the equation. This is called an implicit function. You'll notice that the title of this section is called Implicit Differentiation. It's taking the derivatives of implicit functions, functions that aren't specifically written as a function notation or of y on one side of the equal sign, and then a single variable to the right of the equal sign, normally x. So in this section, we're going to learn to differentiate functions of y with respect to x. We're going to learn how to do specifically the dy dx notation as opposed to the y prime notation. Like when we had functions earlier this semester, like if I had a function of like 3x squared, if I did the long notation, I might have said dy dx is 6x. Well, we're going to learn how to find dy dx for functions that aren't solved for y using something called implicit differentiation. And then, so the theory behind the technique that we're going to use today, it's kind of heady, but we can find the derivatives without completely understanding the theory. So I think I'm going to jump into the technique of implicit differentiation. So implicit differentiation is a method that we're going to use to differentiate for implicit functions. We're going to find dy dx, assuming the variables in the problem are y and x. I'm going to find dy dx for a function that isn't solved for y in terms of x. To compute the derivative using implicit differentiation, we're going to find the derivatives normally, except there's just going to be one difference. That difference is when we find the derivative of a y, we're going to multiply by dy dx. So that's not really anything new, because when I took this derivative of 3x squared, I did the derivative of the right side, which was 6x, and really the derivative of this y is 1, and I took a derivative of a y, and if I'm using the non-shorthand notation, I tacked on a dy dx. So if we're using the long notation for the derivative, I've been doing this all the time. This problem is an explicit function. It's explicitly solved for y, but in some sense, I've been using this strategy. I found the derivative normally, except when we find the derivative of a y term, we tack on dy dx. It's just here, the y term had a derivative of 1, so I didn't show the derivative of the y term. When I get a slightly more complicated problem, like if this problem said 5y equals to 9x cubed, and I wanted to find its derivative, Well, the derivative of the right side, no big deal. The derivative of 9x cubed is 27x squared. The derivative of the left side is 5. And when I do the derivative of a y, I'm going to tack on a dy dx. I'm going to divide both sides by 5 and get this ugly dy dx equals 27x squared over 5, or equivalently 27 over 5x squared. Just to kind of show you that this technique of anytime I take a derivative of a term with a y, I tack on a dy dx, produces the same answer if the function was solved explicitly for y, let me rewrite this problem and do the derivative. So this function 5y that I use implicit differentiation to take the derivative, meaning I found the derivative of 5y. Anytime I take the derivative of y, I tack on dy dx. Found the derivative of 9x cubed, which was 27x squared, and did the algebra and got the derivative was either form of this. These are equal to. The problem that I wrote here, it wouldn't be, this is an implicit function because it's not solved for y. It wouldn't make it hard to solve it explicitly for y. If I would have just taken this function, divided both sides by 5, and maybe wrote the right-hand side in a way that's better for derivatives, then I can take the derivative. Writing the nice notation here, the longer notation, I can say dy dx, and then I'll go exponent times the coefficient, so 3 times 9/5, lower the exponent by 1. And for this 3 times 9/5, I probably should think of it as 3 over 1 times 9/5. Multiply the 3 times 9 and get 27. Multiply the 1 times 5 and get 5, and leave the x squared. So these match up perfectly. This, I rewrote it as an explicit function, explicitly solved for y, and did, I'll call, normal derivatives. This same function written implicitly, because it's not solved for y, but it's pretty close to being solved for y, I called it implicit function. And to do the derivative of an implicit function, anytime there's a y term, we take every derivative normally, except when I find the derivative of a y term, after its derivative, I put a dy dx. That's the whole crux of the section. And the algebra gets messy because the solving for the dy dx could be the ugly part. Taking the derivative, maybe not so complicated, but getting the derivative, so the dy dx, that's going to be the challenge. So explicit functions and implicit functions, if they're equal to each other, are going to have the same derivative. If I have an implicit function and it's easy to write it as an explicit function just by solving for y, then I don't need implicit differentiation to find the derivative. But if in most, if not all, the problems in this section, it's going to be impractical to isolate the y, so it's going to be impractical to rewrite the problem to do explicit differentiation. We're almost going to do exclusively implicit differentiation, and that's just regular derivative with the extra bit that if we take the derivative of a term that has a y, after I take its derivative, I tack on a dy dx. And then my answer needs to be what dy dx equals to. So after I compute my derivative, doing the derivative of the x's normally, doing the derivative of the y normally, but tacking on a dy dx, after I do the derivative, I need to do the algebra to solve for dy dx, and that's going to be my answer. Let me show you how grungy the algebra can get. So this example here, I don't think I could solve it for y very nicely. So I'm going to do implicit differentiation. This is an implicit function. It's not solved for y. I'm going to take the derivative of each term. To the right-hand side of the equal sign, straight derivatives. The derivative of 5x cubed is 15x squared. The derivative of 7x is 7. And the derivative of minus 2 is 0. That's standard. The left-hand side, not so much. The derivative of y squared, to do its derivative, I'll put the 2 in front of the y and get 2y, lower the exponent and get 2y to the first. Because this is an implicit function, anytime I take the derivative of a term with a y, after I take its derivative, I'm going to tack on a dy dx. The next term after the plus sign on the right-hand side is a y to the first power term. The derivative of any first power term is its coefficient. So the derivative of 1y is just 1. And again, because this is an implicit function, I'm going to tack on, anytime I take the derivative of a y, I'm going to tack on a dy dx. In the theory behind this that I really didn't get into, it's pretty heady. I think it's a little bit much for a 212 class, and maybe even a bit much for most 220 students. I need to solve for one dy dx, and I have 2 of them. So the algebra challenge in this section is not going to be taking the derivatives. Those aren't going to be anything new. The algebra to solve for dy dx is going to be the challenging part. And there's about 3 tricks, I think, maybe 4 tricks that we're going to need to solve for dy dx. And one of them is going to be shown on this problem. To get the dy dx solved for, I need to have one dy dx and not 2. And in this case, I have 2 of them, but I'm going to treat this dy dx as a common factor. I'm going to factor it out, and what's going to go inside the parentheses when I factor out this dy dx is going to be the 2y that's in front of that dy dx, and the positive 1 that's in front of that dy dx. Now I can solve for dy dx by dividing by 2y plus 1. And the derivative of this function that wasn't explicitly solved for y is the derivative, which I could write y prime if I care to, is going to be 15x squared plus 7 over 2y plus 1. This fraction could only reduce if the denominator canceled with the numerator. Once you have, and when a denominator has a plus in it, it can't cancel with anything but an exact copy. A 2y plus 1 can only cancel with another 2y plus 1. This fraction's not going to reduce. So on this sheet here, I spent 2 sheets of paper to finally get to this derivative of 15x squared plus 7 over 2y plus 1. Ugliness happens when we have a function that has a product of x and y, and I need the product rule, and this is ugly. So if I want to take the derivative, I'm going to take the derivative of 3x squared, the derivative of xy using the product rule, and the derivative of using 7. I start using nice notation because it's going to set us up nicely for section 4.4. This line isn't necessary, but this is what I'm going to do. I'm going to take the derivative of the 3x squared with respect to x, pretending that this problem is written y on the left-hand side and x on the right-hand side, which it isn't, but if it was, I'm taking the derivative of y with respect to x. So I'm going to take the derivative of each term. I've kind of shown this symbolism a few times this semester just to get us used to it. 2 of the derivatives are freebies. This derivative is going to be 6x, and if I really wanted to, I'm taking the derivative of an x with respect to x. The appropriate derivative symbol here would technically be dx dx. When I'm taking the derivative of an x with respect to x, I would tack on a dx dx for the variable, but that's equal to 1. So the reason I don't show that because it's not necessary, because that's equal to 1. So I'm just going to do the derivative of x as normal. That derivative is going to be 6x. This derivative I'm going to do off to the side. To the right of the equal sign, the derivative of 7 is a constant. It's just 0. So let me, off to the side, or down lower, figure out how to find the derivative of xy. And we should put this in our back pocket, have this derivative just in our notes, because it comes up a few times and I don't want to do it every time. So once I figure out what the derivative of xy is using implicit differentiation, I'm just going to keep this sheet handy, and anytime I need to do this, I'm just going to steal it. If you get to use a note card on the test, this is something note card worthy. This I'm going to need to use the product rule because it's multiplication and both factors have an x. Or both factors have a variable. They don't actually both have an x. But my first factor is x. My second factor is y. Now I'm going to do the derivative of each using implicit differentiation. The first term is just the first power term. Its derivative is just its coefficient of 1. It's an x, so I don't need to tack on a dy dx. The second factor, its derivative is 1 because it's a first power term. Its derivative is its coefficient. But because I'm taking the derivative of a y, I'm going to tack on a dy dx. So my derivative of xy is going to be x times 1 times dy dx, cross multiplying down. Put the plus sign from the formula for the product rule, plus 1 times y multiplying up. So then this is just x dy dx plus y. That's an important deal. I'm going to write this on a separate sheet of paper, that the derivative of just the lonely xy is x dy dx plus y. I think this comes up a few times in the section, and rather than reinventing this derivative over and over, I'm just going to pull this sheet back when I have the need to find the derivative of an xy. So this is all side work that was necessary to help me find my derivative, because right after this, after the derivative of 3x squared, which is 6x, I need to put the derivative of xy, and the derivative of xy is x times dy dx plus y. So now I need to solve this for dy dx, which means I need to isolate the dy dx, and how I'm going to do this is I'm going to subtract 6x and subtract y from both sides, and then I'm going to divide by x. And this is where I have some flexibility in multiple ways that the answer can be written. And there's probably a safe way and a dangerous way to write the answer in terms of when I grade, when I see mistakes. So now I have the function almost solved for dy dx. I'm going to divide both sides by dy dx, and I'm going to show it two different ways. These are both going to be correct answers. So I'm pulling out a separate sheet of paper just because there are two ways to solve for dy dx in terms of dividing by x. One way you can't reduce, the other way you can reduce. So the way that's probably safer is to take each term and divide it by x. It's safer because you won't be tempted to reduce something you can't reduce. Taking the x's on the left side and dividing by x, I'm left with the dy dx. And on the right side, my first fraction, the x's cancel, and I'm left with a negative 6. And the second fraction doesn't reduce. So the y needs to have an x under it. The 6 can be free of the x. If I make big fractions, which is the other way to reduce this, I can't reduce the fraction. This is the alternate way that's acceptable to reduce this to find dy dx. And if you write it this way, and you put the entire right side under a fraction, what you can't do is just reduce the x. The common mistake when students write the answer in the second way is they cancel the x's right now, and they would write dy dx equals negative 6 minus y by just canceling the x how it's written, but that y needs to have an x under it. So if you write it as a big fraction, you can't reduce. If you write it as two small fractions, you can reduce because it keeps the x under the y. But if you reduce the x here, you're losing the x from under the y, so we don't want to write wrong answers. All right. Now a new example of implicit differentiation, which is really strange, but we're going to need it in the next section. So here I'm given a problem, a equals 5r squared, and I'm asked to find dr dt, which means I need to take the derivative with respect to t as opposed to the derivative with respect to x. This is a strange implicit differentiation problem, but it's real similar. So to find dr dt, the derivative of r with respect to t, each time I take a derivative of a variable, because the variable doesn't match up with the denominator here, I'm going to tack on a d that letter dt. So when I do the dy dx, because when I did like the derivative of y and I tacked on a dy dx, this is specifically because I'm taking the derivative with respect to x and the variable that I took the derivative of was a y. In this problem, I'm going to take the derivative using the generic power rule, and because I'm asked to find the derivative in terms of t, I'm going to tack on a d that letter dt. Here, when I was finding the derivative in terms of x, when I took the derivative of something that wasn't an x, I tacked on a dy dx. And let me show you this. So I'm going to take the derivative of this with respect to t, which it just is weird, but we need it for the next section. So I'm going to take the derivative of the left side with respect to t, and I'm going to emphasize that this is 1a, and I'm going to take the derivative of the right side with respect to t. I don't need to emphasize it is 5r squared. So because I'm taking the derivative with respect to t, and neither one of these variables are a t, I need to use implicit differentiation for each of the letters. After I find a derivative, I'm going to tack on a d that letter dt. So on the left-hand side, the derivative of a would just be the coefficient of 1. But because I'm not doing the derivative in terms of a, I need to tack on a d, the variable that I just took the derivative of, dt. On the right-hand side, I'm going to do the derivative of 5r squared. I'm going to go 5 times 2 is 10. I'm going to lower the exponent by 1 to get r to the first power. And because I'm taking the derivative with respect to t, and my variable wasn't t, when I take the derivative with respect to x, and if my variable here matches there, I don't need the dd anything. So when I'm doing the y's, I'm finding derivatives with respect to x. The x's, I didn't tack on a d that anything. Technically, I'd get a dx, but that's not necessary because that's equal to 1. But since I'm taking the derivative with respect to t, I need to tack on any letter that I'm taking the derivative of that's not a t, a d that letter dt. So this gives me dA dt equals dr times 10r dt. So specifically, I don't probably really need that 1. This gives me dA dt equals dr dt, trying to save some room here so I don't go off my screen, times 10r. I'm asked to find dr dt. Well, to find dr dt, I need to isolate dr dt, and the thing that's keeping the dr dt from being isolated is the 10r. So I'm going to divide both sides by 10r, and I'm going to get dA dt over 10r. It's really a 3-layered fraction, so I'm trying to make look a little more presentable, equals dr dt. Let's do another one of these ddt's because they're important derivatives in section 4.4. So same deal. I'm giving you a function. I'm asking you to find dr dt. So even though there's not a t in the problem, I could still find a derivative with respect to t by using implicit differentiation. I do the derivatives normally. And if a derivative was a t, in fact, let me change this problem. Let me do this real quickly. Let me find dr dt for, how about this? V equals 7r cubed plus 5t. If I'm asked to find the derivative with r with respect to t, that means I need to solve for dr dt. The equation isn't solved for r in terms of t. I need to use implicit differentiation. Here, the derivative of v, it's a first power term. Its derivative would be its coefficient of 1. Because the variable v doesn't match up with the t, I need to tack on dv dt, the variable that I'm taking the derivative of with respect to t in this case. The derivative of 7r cubed, I'd go 3 times 7 is 21. Lower the exponent to r squared. And I'm taking the derivative with respect to t. And the variable here is r. So I'm taking the derivative with respect to t. And the variable I took the derivative of was an r, so I'll tack on a dr dt. Last derivative, the derivative of 5t would be 5. And if I want to be specific, I'm asked to take the derivative with respect to t, and the variable here is a dt, is a t. So this one, if I wanted to put the dd part on it, it's d the variable that's in the problem, and then divide it by d the variable that I'm doing the derivative in terms of. This piece is 1, so it wouldn't be necessary to solve for. So now I get dv dt equals 21 r squared. I'm going to write the dr dt next just because I forgot to write it. Dr dt. And then this is just going to be plus 5 because the dt is just 1. And I'm going to solve for dr dt by first minusing 5. And I get dv dt minus 5 equals 21r squared dr dt. Since I was asked to find dr dt, I'm going to divide both sides by 21r squared, get a really ugly looking fraction that I would have no idea how to reduce it, so I'm not going to reduce it. And I'm going to say dr dt is dv dt minus 5 over 21r squared for this. So that's ugly. We're at 28 minutes. We're getting ready to get close to the homework. Let me make a part 2. This video might even spill onto a part 3. I kind of can't gauge how long it's going to take. I feel like I can do it in another 30 minutes, but I might not. But this is all the theory. Now we just need to do the homework.